Hello. So what we're going to look at today is geometric series. So that's adding all of the terms in a sequence and finding out what they all add up to. And we're going to have a look at whether the series that we've got is going to diverge, which means it's not going to reach a specific number, it's just going to get bigger and bigger and bigger each time, or whether it's going to do the opposite, which is called converge. So as the sum tends toward infinity, as in we're taking all of the sums that we could possibly get in that series, does it come to a finite value, like an actual fixed number? So here, our first example, we've got 2, 4, 8 and 16. So if we were going to go through the usual, our first term A is 2, and our value for R, well, we can get that using either terms. So if I considered the second and the first term, 4 divided by 2 gives us 2. I could also consider any sort of consecutive terms. So I could have done 8 divided by 4, that also gives me 2. Or I could do 16 divided by 8, that also gives me 2. So it doesn't matter which consecutive numbers you use in the series, you should still find that you get the same. Now, if we were to consider adding all of these numbers together, so 2 plus 4 plus 8 plus 16, and we went on. Let's say we went as far as infinity. We know that as we went to infinity, that the sum would get bigger with each term. Now, this isn't an official definition, this is just me putting it in layman's terms. So if I wanted to add up all of the numbers that was in that series, what I would find is that it does something which is called diverge. Or we could say it's the divergent series. Because of that reason, as we take the terms and add them all together, it would get bigger each and every time. Now let's consider a slightly different example, the following. So I've got this series 1, a half, a quarter, an eighth, a 16th. So again, let's do the same thing. The first term is going to be 1, and the common ratio, if I have a look at a half and divide that by 1, I'll get a half. Okay, or if I'd have taken the next terms, a quarter divided by a half, I'd get the same, I'd get a half. Now with this, if we consider what happens as we take the sum to infinity. So I'm adding on 1, then I'll add on a half, then I'll add on a quarter, then an eighth, and then a 16th. And then the next term would be 1 over 32, and the next one would be 1 over 64. And if I consider going on, let's say to the 100th term, or the 1000th term, or the 10,000th term, I'm going to be adding on such a small, and potentially insignificant number that really, when I consider adding all of these numbers up together, it's going to tend towards a specific value. It's going to, what we say, converge. It will hit a very specific sum, and the reason for that is because of this value of R. Because the common ratio is a value between 1 and negative 1, that generates a convergent series. I'm going to look at that in a little bit more detail next. Okay, so here's it in a little bit more mathematical sort of writing. If R is between -1 and 1, so not equivalent to 1 or equivalent to -1, it has to be less than 1 but greater than -1. Or for short, we can write that using this modulus function, the way that we do when we're writing the binomial and when the binomial expansion is valid. So then it can be said that the geometric series converges, and let me just show you the proof for how that works. So this is our formula for the sum of a geometric series. And so we've got A as the first term, R is that common ratio. And what we find is that as n tends to infinity, so thinking about that, for the previous example, that was, the number of terms. So I got down to adding something as tiny as like this 0.0001, and I was thinking about the 10,000th term. So as n tends to infinity, what happens to this value of R? Well, the value of R becomes so small that we can say that r to the power of n tends to 0. Okay, so that's this idea here, that it becomes so small that we can just completely ignore it. So if we completely ignore that from our formula, we'll end up with Sn is equal to a times by 1 all over 1 minus r. And we know that a times by 1 is just a, and again, all over 1 minus r. So we can shorten our formula, and if we want to know what a series converges to, this is our formula. So if I go back to that previous example that we had with the 1 and the half and the quarter and the eighth and the 16th, we know that a is 1 and that r is a half. So if we put that into this formula, the sum of this converging series would be 1 divided by 1 minus a half, and that would give us 1 divided by a half. We know that that's 1 divided by a half, which is 1 times by 2 over 1. And so the sum to infinity, oops, I made a little mistake there. So the sum to infinity for this series is going to be 2. And you can think about that, can't you? If you kept adding on the little bit each and every time, eventually all those little gaps will fill up until you're left with just 2 on the whole. So here is an example of how you might be asked to use that formula or to use that information. So we're given that the fourth term of a geometric series is 1.08 and the seventh term is 0.23328. Just make that point a bit bigger. So the first part of the question is asking you to show that this series is convergent, and the second part of the question is asking you to find the sum to infinity. So again, if we think about what makes it convergent, we talked about in the previous slide that a convergent series has got this. So the common ratio is between -1 and +1. So we need to work out what is the value of r to be able to show that this is a convergent series. So let's think about this. If this was the fourth term in the series, that means that my first term was a, I multiplied it by r to get the second term, multiplied it by another r to get the third term, and multiplied it by another r to get to what would be the fourth term. So first, second, third, and fourth. So we have that ar cubed is equal to 1.08. So if we use that same idea now to look at what we get for the seventh term, that would be a times r, so that's second term, third term, fourth term, fifth term, sixth term, seventh term. So that's a times by r to the power of 6. Or we can just use that idea of ar n to the minus 1, can't we? So that's equal to 0.23328. Okay. I'm going to divide these, so I'm going to do ar to the power of 6 divided by ar to the power of 3. So I'm going to get 0.23328 divided by 1.08. So the a's are going to cancel. We know that the powers on this are subtracted, so 6 subtract 3 is going to give us r to the power of 3. And the 0.23328 divided by 1.08 is going to give us 0.216. So that's the value of r cubed. So for me to rearrange this to make r the sum of the subject, I will need to take the cube root of both sides, and ta-da, you will get 0.6 as your value for r. Now we don't need to worry about whether we're taking the positive or negative root, because it's a cube root, it's an odd number, it's just going to give us just the one root. It's not going to be a plus minus like it is with a square root or a fourth root. So we need to just show that this series is convergent, because that's the instructions that we are given in the question. So we'd say that r, which is equal to 0.6, you could write a sentence if you want, so is between -1 and 1. Or you could say something like 0.6 is less than 1, greater than -1, therefore is a convergent series. Lovely. So the second part of the question asks us to find the sum to infinity. So as this is a converging series, we can use that nice simpler version of the formula, which I'm going to write out for you now. So the sum to infinity is going to be that a on its own and 1 minus r. And again, we need to work out what a is actually, don't we? Okay, so ar cubed is equal to 1.08. We know that the value of r is 0.6 as we calculated that in the last one. So 0.6 cubed is equal to 1.08. So that's going to give us 0.216a is equal to 1.08. Rearranging that to get a, so 1.08 divided by 0.216 tells us that a is 5. Okay, so you can check that on your calculator if you'd like to. So my sum to infinity is going to be 5 divided by 1, subtract 0.6. That's 5 divided by 0.4. You don't have to show that stuff with workings out, but it's just nice to. So our sum to infinity will be 12.5. Okay, so what I would like you to do now with your textbooks is I would like you to go to page 75 and try the following questions. So question 1 up to question 8, please. If you do get stuck with any of those, please do just drop me an email and I will write out an example, take a picture of it and email it back to you. Thank you very much.